Hello. Oh, hello.
Hello.
Hope you had a great weekend studying.
Yeah.
Yeah, how's that review going?
I was actually going to ask you about that. I couldn't actually find it.
What?
I don't remember how to get to that folder you were talking about. I've never actually gone back and read over these notes. I've relied on my own notes and the homework problems, so I haven't actually gone back and found that folder. So I don't remember where to find that.
Yeah, so I sent an email and I think it was early October. I want to say October 9th. I don't know why that date is coming to my head here, but I think
So it's going to be an email. I need to go.
It's an email in Canvas. Yeah.
All right. Thank you.
Yeah, look for, I think it says something about, Zoom folder, notes folder, something like that. Should be able to find it. Let me know if you can't. I'll direct you to it. Yeah. Okay. So the review, I know that I've really tried to get y'all to not depend on me for the answers, and I've been stressing everybody out by telling you to work together and scaring you away from me to not ask questions and stuff. So I hope that that's helped you actually learn. I don't know, maybe not, but I will provide you the answers after class, okay? With a little asterisk, I've only gone through it one time and I haven't checked it for any errors. I think everything's okay, but you never know, right? So the main idea of the review is just make sure you've got the essential ideas down of how to do things. And in fact, I think when I did it, because I had no intention of really giving it to you all, I think when I did it, I crammed all the answers in. Like I tried to do all the work. Let me see, where is it? Yeah, like I crammed in all the answers on the page because I didn't want to have to like go somewhere else. So
good Lord.
Yeah, so when you look at this, please understand this is not what I would want you to do when you turn in your exam work, right? I would want it on separate paper, but here it is. So I'll send this to y'all later, okay? It'll be in that folder with the Zoom notes from today. All right, well, we were talking last time about implicit differentiation and how we have this new method of taking derivatives of things whenever we see a function. This was kind of the main idea, is anytime we try and take derivative where we have some function of x in the base and in the exponent happening at the same time, then we have to employ this logarithmic differentiation. And in our notes for the class, there is note 3.3.2, where I actually go through the steps for this, which is you take the natural log of both sides and then differentiate implicitly with respect to x and then solve for y prime. So the steps are there. I thought we'd start class today with an example. This was the quiz that I asked you to do, right? This method. And I only gave you like one or two examples and then I threw you right into the frying pan with it. So I'm curious to see how that went. I think a lot of you got it. So let's go. Let's do one. So let's say that we have some function f of x equals how about x plus 3 to the 5th power times x minus 4 to the 8th power times the square root of x plus 9 all over x squared times 4x minus 3 to the 7th power. That's ugly, right? That is an ugly function right there. And if I ask you to find the derivative of this.
Oh, that's going to be fun.
Yeah, you would not want to even go down the road of quotient rule, right? I mean, think about this. This would be a quotient rule, but when you look at the numerator, you have a triple product, right? If you just try to take the derivative of the top, you've got triple product. So you'd have to do like a triple product rule thing. And then each one of those is a chain rule, right? This is like a complete disaster, right? A complete, absolute disaster. So it also doesn't look like what I just told you. With implicit, I told you if you have a function of x raised to some other function of x and you're trying to find the derivative, then we use this implicit, right? We do implicit. Well, this is not a function of x raised to a function of x, right? That's not what's happening here. So it doesn't look like this is what we would use. Not implicit, logarithmic, sorry, logarithmic differentiation, not implicit. Implicit is part of this, but so we don't have that, right? But it's actually still going to work, all right? And let's go through the problem, and after I go through it, then maybe you'll see what tipped me off to do this, all right? So first thing I'm going to do is I'm going to call the left side of this equation y instead of f of x, all right? Just going to call it y. And now I'm going to take natural log on both sides. So I'm just doing natural log of the left and then natural log of the entire right-hand side. I get to copy paste. There we go, right? That is a legal algebraic move. I have not done any derivatives, right? No differentiation. I'm just using properties of logs right now. Now on the right side of the equation, I'm going to use one property of logs that says this. If we have natural log of, let's say, x divided by y, the property of logs says that I can split that into two logs with subtraction, right? That's property from college algebra. So if we look at the numerator, x, as being that in yellow, and then the denominator being the blue, then for us, the entire numerator, right, is like the x, and the entire denominator is like the y. So I can rewrite this. Again, I'm not doing any calculus here. This is purely algebra. I'm going to rewrite the entire right side using that first property. And I'm going to go ahead and rewrite that square root as to the half power instead. You'll see why in a minute. And that's all over the denominator, the natural log of the denominator. So are there any questions on what I just did using that property on this side? Any questions on that?
When can we use this property?
Anytime you have a natural log and you have division, you can use this property. Now, we didn't have a natural log to begin with. I had to come in with the natural log myself. And I did that because I knew that I would be able to use the property this way. Anyone see where I'm going now?
Yeah, isn't there another property that if there's two multiplied, you can make it two separate logs added together?
That's right. If we have multiplication within a log, we can turn it into addition. Okay, it's this same property, but for multiplication. In fact, if we have three things multiplied, we can turn it into three logs. Okay, so here, when I look at this first log, I have a multiplication here and a multiplication here. So I have three different things being multiplied. So I can take this one log and split it into three separate logs. Here we go. It's going to be the natural log of the first one plus the natural log of the second one plus the natural log of the third one. And these are pluses because that's what the formula says, right? And then on the second log, I have multiplication again between these two. So I can use this property again. However, there's a negative sign out here. Because there's a negative sign there, I need to first split these and then bring the negative through. So natural log of x squared plus natural log of 4x minus 3 to the 7th, close the parentheses. All right.
Could we then bring our exponents out?
We have that third property of logs that says if we have natural log of x to some power n, that the power can come out in front times natural log of x. So anywhere I see powers, I can drop them. Okay, natural log y equals 5 natural log of x plus 3 plus 8 natural log of x minus 4 plus 1/2 natural log of x plus 9. Okay, minus 2 natural log x minus 7 natural log of 4x minus 3. So I kind of did two things in one step here. I brought the 2 down, right? I brought this 2 down. I brought this 7 down, and then I distributed the negative through to each one to drop the parentheses. So all powers are down now, right? You can only do that if you have a log. And the log came from us, right? We brought the log in. Now at this point, we can differentiate. And the reason I'm ready to differentiate now is because I have 1, 2, 3, 4, 5 terms. I can do them one by one. They all have constants in front, right? Which will come for the ride. Like this 5 will come for the ride. The 8 will come for a ride. This will come for a ride. This will come for a ride. This will come for a ride. And then all I'm really doing is taking the derivatives of the log parts. And taking derivative of the log of something is pretty easy. Well, according to what we learned last class, right?
It's just 1 over that, right?
1 over it times the derivative of what's inside, which for most of these, the derivative of what's inside is 1, right? Except the last one. The derivative of the inside of the last one is 4. So remember last class, we said if you have natural log of something, right? And you want to take the derivative, what it winds up being is 1 over whatever's in there times the derivative, I'm sorry, yeah, 1 over the box times the derivative of what was inside the box, which really just means the derivative of the inside over the inside. So here we go. I've got to do now I'm doing the implicit differentiation on both sides, right? So the derivative of the left side is 1, don't forget the left side, is 1 over y times y prime. Now I'm going to use y prime, I'm going to highlight it here. I'm using y prime instead of dy dx, but I could use dy dx here. We all just hopefully understand, I mean dy dx right there for y prime. It's just easier to write y prime, so I'm just going to write it. So that's the left side equals, okay, the 5 comes for the ride. Now I do the derivative of in here, which is 1, over what was in there, x plus 3. Plus 8 times, now the derivative of what's in here, which is 1, over what was in there, x minus 4. I'm using this right here. Plus 1/2 times the derivative of what's in here, which is 1, over x plus 9. Minus 2 times the derivative of what's there, x, which is 1, over x, minus 7 times, now careful on this one, the derivative of what's inside there is 4, and then over 4x minus 3. There we go. We have differentiated, right? The last step is to get y prime by itself. So you're going to multiply both sides by y, right? So that means I'm going to have everything that's in here all of that times y. But what's y? The original function, right? So I've got to get all this and slap it onto the outside. You know, I'm going to put it down here. I'm going to just move all this. That's your derivative. Now, I had some students ask, you know, do you need to do anything now? Do you need to go through and clean this up? Do you have to distribute this through? No, you don't need to, okay? This is good enough. This is the derivative, right? So even though this was a little bit involved, right? Even though it was a little bit involved in the sense that we had to use these properties of logs and all that stuff, the differentiation was easy, right? It was just the derivative of a couple of logs, right? That part wasn't hard. Whereas if we didn't do this, right? If we hadn't done this log on both sides, we'd probably still be working on this, you know, trying to do quotient rule with products and chains and all that. It'd be a disaster. So this is the more efficient way. So any questions on this? What told me to do that now? Now that you know what we did, what kind of tipped me off to that, right? What made me do that? Well, I've got a bunch of multiplications, right? I've got a fraction, right? And I got a bunch of multiplications and I've got a bunch of powers everywhere, right? These are all powers. So I'm thinking, okay, if I bring logs in, I can turn division into subtraction. Anywhere I see products, I can turn them into addition. Anywhere I see powers, I can pull them out, you know? So let's go with the log, right? Let's do the logarithmic differentiation.
So, question.
Yeah.
Would it be reasonable to just, instead of using quotient rule, you use this? I mean, obviously it's not always going to be the easier course, but is it something, could you just use it instead if you're more comfortable with this?
Yeah, I think you might wind up spending more time on something than you would need to. Like,
Yeah,
for example, let's just do it. I mean, let's say we had this. I'll keep it relatively simple like this. Okay. So if we did our standard quotient rule, it'd be derivative of the top times the bottom, right? Minus derivative of the bottom times the top all over the bottom squared. Right? That would be quotient rule. Now, if we wanted to do logarithmic instead, we bring log in on both sides. We could split that into two logs. Division becomes subtraction, right? And now I cannot pull those powers. Notice the powers are not on the whole thing. The powers here, this 2 is only on the x squared. So I cannot do anything with powers here. Same with this. But I can differentiate now. I can go 1 over y times y prime equals. Now the derivative of natural log of this will be the derivative of what's in here over itself, right? Minus now the derivative of what's in here over itself. But don't forget, I have to take all of that and multiply y on both sides. So you're going to get 2x over x squared plus 1 minus 3x squared over x cubed plus 1. All of that times the original thing was x squared plus 1 over x cubed plus 1. So I don't know. What do you think?
That looks like it should come out to be the same.
Oh, it is the same. There's no question that it's the same.
Yeah,
It's just which one do you like?
Yeah, it's definitely faster to do quotient, but like I can definitely see there are definitely times where quotient's going to be faster and easier. But but like it does just work.
It does work though.
They are completely, you could use either one pretty much. And it comes down to which one do you think is going to be easier for you.
Yep.
Okay, cool.
Yep.
It's like the two different limit
definitions.
Yeah.
Yeah. I guess, yeah, there's just two ways to the same end, right? It's just your choice on which path you want to go.
Yeah, because like I can definitely see like with that last one, like this one, definitely you want quotient, but with that last one, that'd be awful to do.
Yeah, you would never, and I'll have students on the test that don't even do this. They're going to try quotient.
Oh.
Yeah.
Yeah, because I mean,
somebody in here will. I promise someone will.
Like I can do it. I know what to do, but that would be a lot, and I guarantee I'd make a mistake eventually on that one.
You'll eat up so much time. That's the thing. You'll eat up so much time on the test doing that. Okay, let's do another one. Not like that. That's kind of like when it comes to the logarithmic differentiation, that's like one type of logarithmic differentiation. And then the other type is what kind of like what I gave you the quiz on. So let's just do one more of those, and then we'll move on to the next idea. Okay. the next major topic in the class. So I'll start off with calling it y, and let's do this. Let's do x cubed plus x squared plus x plus 1 raised to the x squared plus x plus 1. And I want us to find y prime.
Yeah, this one is not as bad as the others.
What's that?
This one makes more sense to me than the others.
Then like the quiz ones?
No, than like the previous examples. Like that
Yeah,
one.
the one I just did before this one.
Mhm.
Yeah, the thing about this one, it should be like an automatic thing that you look at that and go, oh, well, if I need the derivative of that, then I'm going to have to use logarithmic differentiation because I got x's in both the base and the exponent. Like there's variables in both. So you can't use power rule and you can't use the properties of exponential functions, right? We talked about that last time. We have a way of differentiating x to the n. We have a way of differentiating a to the x. In this case, we cannot apply either one of those because in both those cases, you have to have a constant somewhere, right? You have to have either the power is constant or the base is constant. But here we got variables in both. So I'm going to bring the log in, right? Natural log y, and then natural log of all that. I get to cheat. All right. And now I have a property of logs, right? That just allows me to take that whole power and plop it out front. So you get natural log y equals x squared plus x plus 1 times natural log of x cubed plus x squared plus x plus 1, right? And now at this point, I can differentiate because I have a product. So I can do a product rule on the right-hand side. So I take the derivative of the left, 1 over y prime, and now I just carefully do my product rule. So I take the derivative of the first one, which is just 2x plus 1, times the second one, minus, now I do the derivative of the second one, that's the natural log. So are y'all feeling comfortable with this idea that whenever you do the derivative of a natural log, it's just the derivative of what's inside of it over what's inside of it?
You did a minus?
Yeah, wouldn't this be
Yeah,
a
I don't know
plus
why I
instead?
did a minus. Yeah, I'm sorry. So I'm going to take derivative of what's inside, which is 3x squared plus 2x plus 1, and divide it by what was in there to begin with, x cubed plus x squared plus x plus 1. That's the derivative of the natural log part. And then I still have to multiply that times the first function, which was x squared plus x plus 1. And we're done? We box it? Finished? No.
You have to multiply y.
Yeah, not yet.
Multiply by
Yeah.
y. So we have take this and multiply both sides by y. So it's going to go away over here, right? And on this side, multiply by y also. But I'm not going to do y. I'm actually just going to go grab this now. That's what y is. So on this on this logarithmic differentiation, you're always going to have to multiply by y at the end. You always do, to clear out the left side. So you're always going to wind up with the original function just plopping itself down here again. And that's it. I'm just going to leave it like that. I don't know why, but this whole thing with the logs reminds me of something. So when I was in graduate school, I waited tables early in grad school. Then I started working for the university. But when I waited tables, I don't know if you've ever waited tables. There's usually some sort of like employee lounge area, not lounge area, but a place where there's like notes put up like, hey, we're out of catch up today. You know, there's like a whiteboard or something where the manager can put notes up. Hey, no chicken marsala today, whatever, you know. And so I used to go in there and I used to put little math problems on there. And like, you know, just like simple math problems just to see like problem of the day type things. And one day, one of the guys that worked there, he was an engineering major. And I walked up and he had put a problem up there. He had put this one up. X to the 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 X forever equals 2. Solve for X. So find X. So that looks like a really tough problem, all right? It looks like a really tough problem because you've never really done anything like that before where it's X forever. But you can do this completely without any calculus, without anything. All you need to know is properties of logs. So let's just first agree that what we're saying is that if you have X raised to X's forever, it must be equal to 2, all right? And I just need to figure out what X makes that true. So all I'm going to do is take the natural log on both sides. So when I take natural log here and natural log here, then what I can do is I can take the power on this X, which is actually everything there, right? All of that, and plop it out front. So I have X to the X to the X to the X forever times natural log X equals natural log 2. With me? But what is X to the X to the X to the X forever? What does it have to be equal to in order to solve this equation?
2.
It has to be equal to 2, doesn't it?
Yeah.
I mean, even though it's the power here, it's still the original expression because there's an infinite number of them. So that means that this is 2 natural log of X equals natural log 2. And then I can take both sides, divide by 2. I get this, right? And then I can do the reverse of what we did before. If I have a number in front of a log, I can push it up as a power. But that just means that the natural log of X is equal to the natural log of the square root of 2. And if I do E on both sides, I get E to the natural log X equals E to the natural log square root of 2, and the E and the natural log kill each other off. You get X is root 2. So the answer is root 2. So if you take root 2 and raise it to the root 2 and raise it to the root 2 and raise it to the root 2, and you do that forever, you get 2. Weird, huh? Kind of cool.
Yeah, that's a very weird problem.
Mhm. All right, we got to get
It's one you said it doesn't technically require any calculus, but I think it requires calculus brain to do it, even if
Yeah,
you don't
right.
need any calculus math.
Yeah, it's definitely, it's something that if you haven't seen how to do it, you'd probably try a billion things and never get anywhere with it. All right, so we're moving on. All right, none of this logarithmic differentiation is on the test on Thursday, right? None of this is. Right? The review didn't have it, right? So it's not on there.
So
Now,
it'll just be the exponential and then the solving the logarithmic ones.
yeah, I think the last thing on there was there were some derivatives, if I'm not mistaken, there were some derivatives with logs, I mean, with exponentials. Am I wrong here? Where did it end? 13. Yeah, none of this requires logarithmic differentiation. None of it. Could you do some of it with it? Yes, but it's not required. All of this is just chain rule, product rule, quotient rule, along with you knowing what the derivatives of exponential and log functions are. So we are not worried about that for the test, but we are worried about it for the future, right? So now we're going to move on to the next major topic. And this is very important. This topic is extremely important. All right, it's going to come up again in Calculus 2. It's going to come up again in Cal 3. It'll come up again in pretty much any math that you have, because the limit, what we started this class with was like a fundamental concept. If you look at calculus, like as a subject, if you look at all calculus and everything that branches out from calculus, at the heart of it, you'll see the limit. The limit's the heart of all calculus, all right? So we're gonna go back and do limits now again, all right? So you're gonna get upset, but it's important because I'm gonna give you a new rule. And the new rule is gonna make a lot of the limits that we did before that were hard, it's gonna make them very easy. All right, so we're here to talk about what's called L'Hopital's rule. Now, the way it's spelled, it looks like the hospitals or something like that, but it's pronounced L'Hopital. L'Hopital.
Is it
And I've
L'Hopital?
heard- L'Hopital. Yeah, I've heard different things, different stories on this. I'll have to go back because I'm going completely off of memory, and my memory is starting to fail me a little bit. So I believe, if I'm not mistaken, that, and I hope I'm not wrong with this. I believe that L'Hopital actually did not even come up with this rule. If I'm, please, if I'm wrong, I'll check, but I believe he didn't come up with the rule. I believe that he financed the research required to come up with the rule. So it's basically like, you know, back in the day, if you were a mathematician, you know, the rich people, the people in charge of the country, the kings and queens or whatever, would pay you to go study and go come up with something new. And so since his research was financed by somebody else, part of the agreement was that whatever you figure out, you don't get to put your name on it. I get to put my name on it. I think that's what happened here with L'Hopital. I'll go back and look it up. If it's not, I'm sorry, but that has happened a lot in math. So, you know, it's not something random. It does happen quite a bit. It would be kind of like if you were doing research, you know, you're in grad school and you're doing research, and maybe you're at UT Austin, right? And you come up with some big discovery or something. Like UT Austin is going to get credit for that. Yes, your name will be on it, but you know, you were in their labs doing research under their umbrella, right? Same sort of thing. Okay, so L'Hopital's rule. This is a very, very powerful rule. And I want to remind you of a few limits before we actually get the rule. So do you remember this one? Limit x goes to 0 of sine x over x. So like, I know it's been a while since we've done limits, but remember the first thing we do with the limit is we just kind of try and plug the number in, see what happens. So if you plug in 0 for x, you get sine of 0. So the top heads to 0. The bottom, well, x is headed to 0. So 0 is 0. And we said this was bad, right? And so that meant that we need to do some algebra or some trick, right? Something to do this, right? This all look familiar to you? When I gave you this, though, this limit, I told you, hey, everyone, memorize this one, though. Right? I said, remember this one because I can't prove to you why it's this, but I said the answer is 1. Do you remember me telling you that? I said, just remember that. I said, later on in class, I'll show you why it's 1, but not yet. All right.
I remember you telling
Invited
us
you-
that, but I didn't
Yeah.
actually remember that until just now.
Yeah, I even invited anyone to come to my office because I said I could prove it, but it would be a very, very long proof to prove this is 1. Using something called the Squeeze Theorem and a bunch of geometry. You can prove it, but now I can prove it real easy using L'Hopital's rule. So here's the rule, all right? The rule says this. The rule says if you're taking a limit, all right? And it really doesn't even matter what is going to what, okay? You could have x going to 5, you could have x going to 0, you could have t going to infinity. Does not matter what the limit is, okay? Like what's headed to what, okay? You just have a limit and you have a ratio of 2 functions, f over g. Whatever that is. You could have function on top, function on bottom. It says if you do this and you get 0 over 0, or you get positive or negative infinity over positive and negative infinity, right? So in either case, if you ever see 0 or 0, or you see a positive or negative infinity over a positive or negative infinity, then here's the conclusion of the rule. Then if the limit exists, because not all limits exist, if the limit exists, it is equal to this. The limit, same thing, whatever's going to whatever, of f prime of x over g prime of x. So if you're taking a look at a limit and you're like, okay, this over this, you do your limit, you get 0 over 0. You're like, oh, that's bad. I need some algebra. Or you get infinity over infinity. You're like, oh, bad. That's neat. I need some algebra. Now what you can do is you can look at another limit instead of this one. You can look at a new limit, which is the derivative of the top divided by the derivative of the bottom. Now, if this limit exists, it will be equal to this one. That's the rule, all right? And that's very powerful. So let's do it on this problem, okay? For our first example. So for our first example here, if we take the limit as x approaches 0 of sine x over x, we already know that we get 0 over 0, right? We get 0 over 0. So we know it's bad. We know we need to do some algebra, right? But what we know by L'Hopital is that if this limit exists, if the actual limit exists, which we know is 1, right? We're acting like we don't know that, but the limit does exist, okay? If it does, then it will be equal to, okay, so this is equal to the limit as x approaches 0 of the derivative of the top. What's the derivative of the top?
Cosine x.
Cosine x, and derivative of the bottom?
1.
1. All right, now, as you let x go to 0, cosine of 0 is 1, right? So now you get 1 over 1, and the answer then is 1, and you're done, okay? Now, that seems too easy, doesn't it? Doesn't that seem too easy now?
Yeah, it does.
When I did this, right? When I went from here to here, I used L'Hopital's rule, didn't I? I used L'Hopital's rule. But you wouldn't know that if you were just looking at my work, right? If you were just looking at this, let's just say you picked up some random piece of paper and you looked at it, you said, oh, what did they do there, right? There's no indication that I used L'Hopital's rule. So what we normally do to let people know that I just used L'Hopital's rule, and this is what most textbooks do, is right above this equal sign, they put an L. And that lets everyone know, oh, I'm using L'Hopital's rule. Now, there's nothing that says you have to use L. I've seen some books use L. I've seen some books put an L and circle it. I've seen some books put an H and circle it, or just an H. I personally use an H and I circle it. I don't know why, I don't remember where I saw it, but that's what I always use, all right? But you need to do that to indicate that you've used the rule, right? Somewhere you have to indicate that. All right, so that's it. Okay, let's go. Let's do another one that we did. One of the first limits we ever did in this class. Limit x approaches 2, x squared minus 4 over x minus 2. So if we take this and we look at it, we go, okay, well, what happens if I try and plug in 2? Well, I get 0 on top and 0 on the bottom. Do y'all remember how we would do this one? Without L'Hopital?
Factoring.
Yeah.
Factor, right? We just factor out the numerator, cancel. But hey, you know what? We don't need that anymore. We're going to use L'Hopital. Okay? L'Hopital. So I've gotten on my homework videos, you'll hear me. I always sing that little L'Hopital. I've been doing that my whole life, that I've been doing L'Hopital's rule. I don't know why. Just when I use it, I like to just kind of sing it at the same time. I don't know. Can't tell you why. It's such an awesome rule. Okay, what's the derivative of the top?
2x.
2x. What's the derivative of the bottom?
1.
1. Okay, now just plug 2 in. What do you get?
4.
4. Okay, that's our answer. Now, if you don't believe that, do it the old way. You'd factor the top, difference of squares, cancel factors. Now let x go to 2, you get 4. Same answer. Not a coincidence. That's what L'Hopital's rule gives us. All right.
Man, I thought limits got pretty easy, like just in my head towards the end of us doing them. And holy crap!
Yeah, this is going to be a game changer. So look,
to echo Ricardo, this is awesome.
Yeah. How about this? You'll probably remember this, and these sucked. Okay, watch. Sine 3x over tangent 5x. So when we did problems like this is way back in the beginning. let me see, maybe I can find it quickly. This would have been in probably September. Let's see. This looks like it. Yeah. Okay, so let me do one day before this. No, September, August, maybe last day of August. Yeah. Okay, so something like this where you have sine of x over 4x, x is going to 0, you get 0 over 0. This is where we're trying to get it to look like sine of junk over junk, and the junk goes to 0. And we had to like make something appear so that it would work out the way we wanted it to work out. Do you remember these? A lot of students struggle with this idea. You know, like, oh, okay, I'm going to split it up. Oh, I'd really like there to be like a 4x up here. So I make a 4x up here, but then I need to put a 4x down here. And then I slide the x over here, but I need a 5. So I need to like introduce a 5 over 5. Remember all that?
Oh, the whole
It's like
multiplication by
messy.
one brick.
Messy stuff, right? So now let's see if L'Hopital will save us from this. So if we do our limit right now, x goes to 0, of course, sine of 0 is 0, and tangent of 0 is also 0. So I'm allowed to use L'Hopital's rule here. So I'm take the limit. Now there's some derivatives involved here. So I take derivative of the top, which would be cosine 3x times 3. Don't forget chain rule, right? You have to use that chain rule. And then over, now I need the derivative of tangent 5x, which is secant squared 5x times 5. Chain rule again, right? Like you do need to know what the derivative of sine and tangent are here to do this. But the good news is that now when I plug 0 in, everything is good. Like if I plug 0 in here, 3 times 0 is 0, cosine of 0 is still 1, and so the top just becomes 3. And then on the bottom, what is secant of 0? Secant of 0 is really 1 over cosine of 0. Isn't that what that is? That's what secant is, right? 1 over cosine. So secant of 0 is 1 over cosine of 0.
Yeah, so it'd be
Cosine
1
of
as
0 is
well.
1. Yeah, so that's 1 and then squared. So 1 squared is 1 and just hit it with a 5 and you're done. 3/5. No magical thing we have to put in there and see something and junk over junk. Don't need it. So the natural question that I get from students is, why didn't we just do this from the beginning, right? Like, why not just do this from the beginning? And why do we have to suffer through all that? Well, why?
We need to learn how to do derivatives first.
Yeah, you don't know what a derivative is, right? So like back in the beginning of class, if I would have told you, oh, okay, just use L'Hopital, just take derivative top and bottom, you wouldn't have known. This is one of those really cool times in math where when you think about the path that we traveled, we started with the limit in the class, right? And from the limit, we actually came up with this new idea called the derivative, right? The derivative. And the derivative, with all this, we can do equations of tangent lines and all this other stuff, right? And then we go, oh, wait a minute, hold on. L'Hopital, or whoever paid L'Hopital, whatever it was, whoever L'Hopital paid, they realized, you know what? We can actually use that derivative to come back here and do limits now. So we couldn't do it before. It wasn't that we were trying to hide it from you. It's that we just couldn't do it because we didn't know what derivative was. We didn't know a derivative. We didn't know any of the rules, power rule, quotient rule, chain rule, product rule. We had no idea of what that was. So you would have not known what to do, right? But now we have it, and we can use it. Now, sometimes it takes a little work. All right, so let's do another example. Let's say we have limit x, let's go to infinity. X goes to infinity of x cubed plus x squared plus x plus 1 over x cubed plus x squared minus 4. Let's do that. So what happens when x goes to infinity here? What do we get? Where's the top headed? Where's the bottom headed?
They're both headed to infinity.
Both to do infinity, right? Infinity over infinity. So L'Hopital says, all right, that's cool. We got that. 0 over 0 or infinity over infinity. You can use the rule. So this should be equal to, by L'Hopital's rule, I'm going to use an L just for fun. You know what? Now I think about it. I think the book uses H. I can't remember. Doesn't matter. L or H, doesn't matter. I switch back and forth. All right, so now derivative of the top, 3x squared plus 2x plus 1 over 3x squared plus 2x, right? Okay, well, this is the first time this has happened. We did it, and it actually did not give us something nice, because if we let x go to infinity, we get infinity on top, right? And infinity on the bottom. We're not getting a nice answer.
Could you just do it again?
Yeah, let's just do it again, because look, it doesn't L'Hopital's rule say if this limit exists, then the derivative, if you take the derivatives of the top and bottom, whatever that is, that is. So it's like a chain. It's like, I'm going to do L'Hopital again.
So just keep doing it till we don't have an x anymore, basically.
Keep doing it until you can get an answer. Until you can actually, right now we're still at infinity over infinity. We must stop as soon as we don't get that. Okay, so let's do the derivative again. What do we get?
6x plus 2 over 6x plus 2.
Over 6x plus 2. Okay,
Yeah.
so what I'm saying here is don't do it again. Don't do
Because that's
L'Hopital
1.
again, because that's 1, right? You want to stop as soon as it's something you can get the limit of. This is 1 because algebraically that is just 1. So your answer is 1. See, you could go crazy. Don't do this. If you did L'Hopital again, let's just say, you would get what?
6 over
6 over
6.
6, which is 1, but what if you did L'Hopital again?
0 over 0.
You get 0 over 0, and then you start to like screw things up. You have to stop as soon as it's something that you can do. You only continue it when it's infinity over infinity or 0 over 0. Understand? Okay, let's do this one. Limit x goes to infinity, x cubed over e to the x. Where's the top headed?
Infinity.
Infinity, right? Infinity cubed is infinity, and then e to the infinity.
I think that would also be heading to infinity.
It is. Let's make sure we all understand why, though. When we say e to the infinity, we're saying take a look at the function e to the x, right? This is e to the x. And we want to know what happens when that x goes to infinity. So what happens when you go out to the right? Where does the function go? It takes off to infinity, right? So as x goes to infinity, the function takes off to infinity. So we get infinity over infinity. I can use L'Hopital. L'Hopital, I'm going to do L's. I think I'm one L's here. Derivative top 3x squared over, what's derivative e to the x?
E to the x.
EX,
Oh, right, just itself. Okay. Are we getting infinity over infinity again? Okay.
Yeah.
L'Hopital. 6x over e to the x. Infinity over infinity. But what's happening? We're chipping away at the powers on top, aren't we, each time? Six over e to the x.
Infinity over 6, which should be 0.
6 over infinity,
Yeah, 6 over infinity, which should be 0.
which should head to 0, because now what we have is a fixed number on top over something that gets infinitely big. That's when we stop. Fixed over infinity goes to 0. Okay? So this is a really nice rule, okay? And you'll now have the opportunity to practice problems again and use the rule. Sometimes, now look, I want you all to understand something let me be very clear on this. It looks by the examples that I've given you that every time you use L'Hopital's rule, everything gets better, okay? That's not always the case. Sometimes when you start applying L'Hopital's rule, it actually gets worse. Like you take the derivative of top and bottom, and then it starts to get more complicated, more complicated, more complicated. In that case, you probably would chunk L'Hopital and go back to something more traditional like what we started the class with. Just fair warning, I don't want you to think that the L'Hopital is like the cure-all, the magic pill that cures all limits. It helps out tremendously, but there are limitations to it. All right. Well, just like everything else in this class, as soon as we get a rule that helps us, right, we start doing harder things. So now let's start looking at other limits that are more challenging than this. All right. Things we have not done. In fact, if you go back to our formula sheets, right, the limit summary, remember this? This good old thing. We've done everything in yellow. Yeah, we've done everything in yellow. We have not done this or this or this or this or this. We have stayed away from limits that do these things intentionally. The reason we've stayed away is because really you can't do them without two things. You need logarithms and you need L'Hopital. Once you have logarithms and L'Hopital, you can do the things in green. So let's take a look at our first example. Okay, let's take a look at it.
I think we did an infinity minus infinity.
I think we did. We
once.
factored. I was kind of thinking about it. I think we did. We factored, but we'll be able to do it with this.
I think it was the hardest one we ever did, though.
Probably. So in the notes, it talks about this in our notes for the class. It talks about, here are some new indeterminate forms, right? We already know 0 over 0 is bad, and we know infinity over infinity is bad. L'Hopital can handle those now. But now we're going to look at these new forms that are bad. All right, these are new forms that are bad. So let's take a look at one. All right, isn't this exciting? All right, so here's an example. Limit as x goes to, let me see. Let's let x go to 0. And let's do, I'm trying to think of how one does. Let's do x times natural log x. And you know what? Let's go to x from the right because I can't come to 0 from the, sorry, let's approach 0 from the right because I can't come in from the left because I have a natural log in here. All right. So before we do this problem, I'm going to go graph this as a function, x natural log x. Curious to know what it looks like. X times natural log x. All right, so what does it look like is happening on this function when I approach 0 from the right? So I'm coming in, where am I headed?
Up towards 0.
To 0, the y value, right? So remember, this is, when we were talking about limits, we're approaching 0 here from the right. So we're walking along this function, coming in from the right, and we're trying to measure our y values. Where are our y values headed? It looks like 0, right? Looks like we're headed to 0. Okay, we need to prove that. Because when you look at the limit itself, let's talk about what's happening to the limit. So when I take this limit, where is this headed? If x is headed to 0, then x is headed to
0.
0, right? Now, am I saying that x is 0 right now? This is very important. Am I saying that x is 0?
No, it's approaching.
Just that it's really close to 0, right? So imagine I have this very, 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 very infinitesimally small number, right? Tiny little number. And I want to multiply it times this number. Well, what does the natural log function do as you head to 0 from the right? Well, you got to know what natural log looks like, right? We talked about this a class or two ago. This is what natural log looks like. And so where's the natural log function headed as you approach 0 from the right?
Infinity.
Negative, right? It's headed to negative infinity.
Yes.
Right, it's diving down. Y'all with me? So this is headed to negative infinity. So what does this mean? You have to really understand what this means. We are not saying take the number 0 and multiply it times negative infinity. Because first, negative infinity isn't a number, it's an idea, right? The idea is that this number right here, when I start letting x get close to 0, this number right here is getting really big and negative. Like really big and negative. And I'm multiplying it, not times 0, but like times a really, really small number. So who wins, right? Who wins? If I tell you right now, I've got this really big number and I'm multiplying it times this really small number, you won't be able to tell me anything about the answer. Because you have to know exactly like how big, right? How big is that big number and how small is that small number? Without any like real indication of the size of those things, you can't tell me. So this is why this is an indeterminate form. Just like 0 divided by 0 was indeterminate. We couldn't tell what it was just by looking.
So
Same
question,
idea. Uh-huh.
what if it was not a limit and this was 0, like true 0 times actually infinity? Would it just zero out because of 0 or?
Well, if this was truly the number 0
Yeah,
times, you would have to multiply it times another real number. So infinity is not
Okay.
a real number.
you can't just multiply it by infinity, right?
But 0 times any real number should be 0.
Okay,
Right? So if you give me 2 real numbers, you tell me one of them is the number 0 and the other one is a really, really big, big, big number, multiply them, I'll tell you the answer is 0.
yeah, of course, okay.
But if you don't
But
tell
you,
me.
you can't
well,
just
tell me-
multiply it by infinity because infinity is not a,
It's a concept, right? It's an
yeah, it's
idea
not
that
a,
the
not
number's
an
getting big.
actual real number.
Yeah.
Gotcha.
All right, everyone good with the idea that we have work to do here? That there's, right now, we cannot tell what the answer is. All right, there is a standard way that we approach these problems, all right? Anytime we see this, here's the standard approach. You take the limit, okay? And what you're gonna do is, you see how we have two different things here? We have an x and we have a natural log of x. We are going to take one of them and drop it to the denominator. Now, which one you choose is up to you, but a lot of times one is way better than the other. So what do I mean by drop to denominator? Just watch. I'm going to leave the natural log x there, and I'm going to write the x that was out in front as a 1 over x on the bottom. Now, I have not changed anything in this problem, right? Because x out front is the same as putting a 1 over x on the bottom. A 1 over x on the bottom would flip back up and the x would be back on top, right? So this is the same thing. But now if you look at the numerator and denominator separately and take the limit, where does that go? Where did we say that goes? If you plug 0 in or try and get close to 0 from the right of natural log, it goes to where?
Infinity, negative
Negative
infinity.
infinity. Okay. Over, now look at that whole thing together as one piece. What happens when you have a fixed number on top and the bottom goes to 0? What happens to that number?
It approaches infinity.
It gets big, right? Fixed over 0, like it's headed to 0, right? X is headed to 0. So you have a fixed number on top, a number on the bottom gets smaller, that ratio gets big. So now the bottom goes to infinity. And so do you see now you have something that looks like infinity over infinity instead of 0 times infinity? All it is, all we've done here is just like massaged it, okay, and made it look different so that we could apply the rule. So now here comes L'Hopital. Derivative of the top. What's derivative of natural log x?
1 over x.
1 over x. Okay, now careful, careful, careful on the bottom. What's the derivative of 1 over x? Just remember, 1 over x is really x to the -1. I want that derivative, so the derivative should be -1 x to the -2, which is really -1 over x squared, right? That's what derivative of 1 over x is. People will tell me that students will make the mistake and they'll say the derivative of the bottom is 1. And they like completely forget, like, wait a minute, it's not x, it's 1 over x, right? So you just bring the x up and do a little power rule. So the bottom is -1 over x squared. Now, before you do anything else, just algebra, right? You have a fraction over a fraction. So we flip it up. and we get 1 over x times, bring it up, it'll be x squared on top, -1 on the bottom. And algebraically, one of the x's cancels. And you just get negative x here. That's all that's left. And let x go to 0 now. And if x goes to 0, well, -0 is still 0. So that should be the limit. So on a test, okay, not this next test, but on the next test after that, which is I think the final, right? If you do this right here and you say, oh, 0 times anything is 0, and you put 0 here as your answer, I'll give you 1 point for showing up, okay? But I'm taking 9 away because that's luck. You just got lucky. You have no idea what's going on here. You understand? Like you have to go through this work. The answer is not always going to be 0. It depends on the functions. It really depends on how fast these things are getting small and getting big. All right.
Yeah, because any slight change on any of this would throw the answer off from 0.
Mhm.
It's really just a coincidence that it just happens to be that.
That's right. Let me see here. Try and think of.
Wait, I wanted to ask real fast because I feel like I might have missed this, but the 1 over x, how does that go to infinity again?
Okay, so what we're doing is you're talking about this part right here when I'm taking that limit, right? If you just look at it by itself as its own little problem. The idea here is that the top is fixed and the bottom is headed to 0. And anytime we have that, it's either going to be positive or negative infinity. Right, because the bottom is getting smaller as the numerator stays fixed. If it helps, just think about the graph of that from college algebra. It looks like this. So as we head to 0, it doesn't matter which side we're even coming in from, it's taking off. The function's asymptotic at 0. But I think it's better in a calculus class to just think of it this way. Fixed over something going to 0 takes off to infinity. All right. Let me try something here. Let me just think about this for a second. Trying to think if we should do another one of these. We should. How about this? Limit x goes to infinity of x times sine of 1 over x. And let's make it x. Yeah, let's just make it x. I don't want to make this crazier than it has to be. First things first, let's figure out what's happening. So as x goes to infinity, this is headed towards infinity. And then what about this whole sine thing? Where's that headed?
Wouldn't that be 0?
It's headed to 0, right? Now, the reason it's headed to 0 is because 1 over x, right? The x is getting big. So we have fixed over big, fixed over infinity. That heads to 0, and then sine of 0 is 0. Right? This is an indeterminate form. We're not going to say the answer is 0. We're actually going to do L'Hopital. Well, we can't do L'Hopital yet. We have to do what first before L'Hopital?
Put one of them on the bottom.
Put one of them on the bottom. The one that I think is easy is, again, the x, because it becomes 1 over x on the bottom. Right? Okay,
That's
now
0 over 0.
we get 0 over 0. If I take that limit on top, it still goes to 0. The one on the bottom goes to 0. 0 over 0, L'Hopital. L'Hopital. Be careful on the derivatives now. When you take derivative of sine of 1 over x, you're going to have chain rule there, aren't you? Some chain rule. You're going to have cosine of 1 over x times now the derivative of the inside and the derivative of 1 over x. We just did that a second ago, right? It's the same thing. So it's negative 1 over x squared. All of that over the derivative of the bottom, which is 1 over x again. So we're just going to get negative 1 over x squared again. And that's really nice, isn't it? Because those go away. And now I can let x go to infinity. 1 over infinity goes to 0, and cosine of 0 is 1.
1.
See, this is weird because here you can't accidentally get it right. Like 0 times infinity, you know, it's 1. Like, I don't know how you're going to get that without doing some work. Here, you might have got lucky, but see, I always look at it like a tug of war, right? It's like a tug of war. You've got one of these guys is like, hey, I want to be really, really small. And this guy's, well, wait a minute, I want to be really, really big. And they're fighting with each other. Who's going to win? In this particular case, this x factor won, okay? It dominated the natural log and it won over, okay? As x got closer to 0, this thing squashed down to nothing. But in this problem, one of them wanted to get big. The other one's like, no, I want to be small. And they're like, no, come on. They're going back and forth. And neither one of them wins, right? This guy doesn't get to go to infinity. This guy doesn't get to go to 0. It's almost like they compromise and they're like, okay, we'll just go to 1, okay? That's where we're headed. We can graph it. X times sine of 1 over x. Now remember where we're headed. Where were we headed in this problem? We're headed to infinity, right? Not to 0. So in the middle, there's a lot of crazy stuff happening here. In fact, if you try and go to 0, the limit as x goes to 0, that limit doesn't exist. There's too much crazy stuff happening there. But as we go to infinity, it means if we go out to the right, you can see that that it is approaching this horizontal asymptote y equals 1 as you go out to infinity. It's getting closer and closer to it without actually ever getting there. So they compromise. That's good. You know, we need more compromise these days, don't we? All right.
I gotta say, what it's doing at 0 is impressive.
Yeah, it's crazy.
Those ones that just start freaking out infinitely at some point are fun.
Yeah, there's something. If I take the x away, it's just as bad. The way you can try and understand this is that if you go back and think about the sine function from pre-cal, when you look at the sine function in pre-cal, sine, maybe this will ring a bell. If you put something in front here like bx, this b somehow controls your period, which is how often you get one cycle of the sine function. So if you do something inside where this thing somehow becomes infinitely big, so as x goes to 0 here, right? As x goes to 0, this inside argument becomes infinite. What's happening is it's like it's trying to draw the sine function, right? But as you get closer to 0, it's trying to draw more sine periods. As you get closer and closer to 0, you're trying to draw more and more and more. So it's like trying to infinitely squeeze an infinite number of sine curves in there as you get closer to 0. It's funky, but it is what it is.
That's interesting.
Okay.
I hadn't actually thought about it, but that makes a lot of sense.
Yeah, it's just you're just making the period go nuts in a very small window. All right. I'm wondering if we're ready for the next. Let me see. It's 2:09. We are kind of ready for the next part. Want to jump to something real quick. I should have had this ready to go, but I was gonna try and bring up something from my Cal 2 class where they had a, nah, it's gonna take me too long to find it. We had a problem in Cal 2 the other day where we had to do something like this. So let me try and remember it. It was t goes to 0. Hold on. No, it was infinity. Yeah, okay. I think it was something like this. We had this in the, it was limit. It was t goes to infinity. So we're using t instead of x, but still just a letter. And it was like t squared e to the negative t. That's what it was. T squared e to the negative t. So that limit just kind of popped up in the class, like at the end of a problem, we needed to do that. And so you look at this and you're like, okay, what the heck is going on here? There's kind of two ways to look at this. One way is, okay, let t go to infinity. This thing would go to infinity, right? T squared goes to infinity. And then what does this e to the negative t do as t goes to infinity? E to the negative t, what does that do? So you have to know what, go ahead.
Approaches zero.
Yeah, it would
approaches
approach zero.
Yeah, so
Yeah.
how do we conclude that? Well, here's what we'd have to do. There's kind of a couple of ways to look at it. If this is e to the t, that's what the exponential function is. We don't want to know what happens as t goes to infinity because there's a negative sign here. We want to know what happens to this curve as we go to negative infinity, which means we want to go this way, and you can see it dives down towards 0. So that heads towards 0, and so you get infinity times 0. And that is an indeterminate form, right? So I'm going to drop one down. Which one do you want to drop? I mean,
E to
we've
the
been
negative
dropping the
t.
nice one, right? Like we dropped the x last time and kept the more complicated one up.
Let's drop,
Here,
let's
I'm
drop
gonna-
e to the negative t.
I'm going to drop the e to the negative t. And that's mostly because the derivative of that's easy, right? So if I leave the t squared up and drop the e to the negative t down, it'll become e to the positive t on the bottom when I drop it down. And now a quick check, this goes to infinity. That goes to infinity. And I can use L'Hopital. Derivative of the top, 2t. Derivative of the bottom is itself. Got to do it again because I've got infinity over infinity. So I've got to go one more time. Two over e to the t. And now I have fixed over infinity, right? Fixed number 2 over infinitely big. That goes to 0. Okay.
This can be one of those stupid simple question again, but why does when e go to t goes down, why is it become positive?
So that's just properties of exponents, right? So when you have x to the negative n, that's the same as 1 over x to the positive n, right? So like if you had x to the negative 2 power, that's the same as 1 over x squared, yeah? So same thing, e to the negative x is the same as 1 over e to the positive x. Yeah. So I've done this before. I don't recommend doing it, but if you've ever gone to HEB or one of these, you know, grocery stores or whatever, and you've gone to the deli market to go get some, like, you know, roast beef or ham or something, right? Go ask the person for 2 to the negative 1 pounds of roast beef and see what they say to you, right? What is 2 to the negative 1 pounds?
1/2.
Yeah,
It's half a pound, right? That's just the same as 1/2 to the first power. It's half a pound, right? So go ahead and do that and see if they actually give you your telemeter. They tell you to go to hell, right? 2 to the -1 is just 1/2, right? It's a complicated way of writing the number -1/2. I mean, sorry, positive 1/2.
I'm gonna do this at work. I'm gonna like test the engineers, see if they remember.
Yeah, if they're engineers, better remember what 2 to the -1 is. All right. Okay. So if we have 0 times infinity, it's an indeterminate form. We'll take one of them and drop it, right? And then hopefully from there, we can work something out. Yeah. Let's look at the next indeterminate form, right? Because there's more. There's more. Go back to your formula sheet. We have talked about now that. Let's do this one. 1 to the infinity. 1 to the infinity.
Oh, no.
I'll start with an example of 1 to the infinity. So limit x approaches, let's go to infinity. And then let me do, I want to do 1 to the infinity. So let me do this. Let me do cosine of 1/x, all that raised to the x. Let's talk about what's happening here, right? Let's talk about what's happening. As I let x go to infinity, this yellow part, 1/infinity, is headed to where?
0.
0. Now, is it 0, Emily, or is it? I don't know. I think Emily said that. Is
Yeah,
it 0?
it's, well, technically because cosine would be 0, it'd be like 1.
But is 1/infinity equal to the number 0, or is it a number really close to 0?
Really close to 0.
Really close to 0. Is everyone clear on that? In the limit, this 1/x is a really small number, close to 0. And cosine of a number really close to 0 should be really close to what?
1.
1, right? Because cosine of 0 is 1, right? But we're not at 0. We're really close to 0. So what you need to understand is this number right here is headed to 1, right? But please, I'm not telling you that it's 1. I'm telling you that it is getting close to 1, right? Close to 1. Not 1, close to 1. It could be 1.00000000000000001. It's really close to 1, but it's not 1, right? And then you have the power here. And where's that power headed?
Infinity.
Off to infinity, right? Off to infinity. So you're trying to take this number and raise it to an infinite power. Now, I really do need you to understand this. This is like what we just talked about in the previous problem. If I right now, just clear your minds for a moment. If I say, hey, everyone, here's the number 1. What's 1 squared?
1.
1, 2 squared, 1 cubed, 1 to the 4th, 1 to the 10th, right? 1 to any power is 1. I totally agree with that. But that's not what we have here. We have a number that's really close to 1 being raised to a power that's getting bigger and bigger and bigger. So it's like the base, okay? The base and the exponent are fighting with each other. It's a tug of war again. The base is like, I really want to be 1. Please let me be 1. And the exponent's like, no. I'm going to multiply you times yourself over and over and over and over and over. Who wins? Okay. Does the base get to be 1 like it wants to, or does the exponent overpower it? Understand? I always remember this sort of example because many years ago, I had a student of mine call me like 3 years after they took Cal 1 with me. And they were in school at like Texas A&M or something. And they were like, hey, I remember when we were doing limits, like you told us that like 1 raised to the whatever was something. And I was like, I never said the number 1 raised to the infinity. I guess what they confused was the idea of, is that actually the number one or is it a number close to one? And they thought that this was the number one. And so they were trying to make a problem much harder than it had to be. The problem that they had, it was the number one, and 1 to any power is 1. But if it's a limit and the number's close to 1, it's a totally different story. So please understand that, because I don't want you to call me in 2 years complaining about something you didn't understand. All right.
So if this actually was actual 1 to the power of infinity, it would just be 1.
Well, again, you can't say to the power of infinity.
Yeah.
But you could say if it was the actual number 1 to any power.
Yeah.
The answer would be 1.
Okay. So if this wasn't a limit, it would just be 1.
That's right. So
No.
on that formula sheet, I mean, the limit summary that I have, where it has all those different forms, 0 over 0, infinity over infinity, all these different things. All of that is based upon if you see that in a limit. If it's in a limit that you see that, then you can do these things. All right. And I thought I heard another question. Is there another question?
Yes. Now, won't this behave really differently depending on whether we're approaching 1 from the left or from the right? Because if it's less than 1 and approaching 1, it should shrink as it's exponential from the exponents, right? Whereas it will increase if it's right of 1.
That is okay. So, all right, let me try. I'm going to try and help everyone understand your question. This is a great question. Let's look at just cosine of 1 over x. Okay. There's cosine of 1 over x. Let me take the other stuff out of here. Where were we approaching, Josh? What were we approaching? X was approaching what?
X was approaching 1.
No. X
but
was approaching
from-
infinity, right?
Oh yeah, X was approaching infinity.
Okay, so if I go cosine of 1 over x, right? 1 over x, this is approaching 0, right? Right, and so here's the picture of this graph right here. Look at where we go. Look at what this function is approaching as we go out to infinity. It is approaching 1, right? It is approaching 1, but these values are bigger or smaller than 1. This is what Josh is getting at, right, Josh? Am I correct?
Yes.
So we are approaching 1 from which side? Like here's 1. These values are what? Really close to 1, but are they actually ever 1?
No, they're all smaller. But it
Josh
should
is saying
be.
they're a little smaller, aren't they?
Yeah, and it
they're a
should be
little smaller.
smaller all the way until infinity because they'll never actually reach.
It never actually reaches. So with that understanding, what do you think is going to happen here, Josh? Because these numbers they're close to 1, but they're smaller than 1, and then they're going to get these bigger powers.
I think it'll decrease towards 0.
Probably
I don't know if it'll
0.
go.
Yeah, let's see.
Because-
let's do it. Let's do it. Right. The big thing is right now, we don't know, right? It's just 1 to the infinity. That's something we got to work on. The question is, how are we going to bring L'Hopital into this, right? L'Hopital only works if we have 0 over 0 or infinity over infinity. That's the only time L'Hopital works. We already know from the last problem that if we see infinity times 0, right? If they're multiplied, then we drop 1, right? Here we drop 1. But we have not seen this form yet. 1 to the infinity. Haven't seen it. So how do we deal with it? Well, here's how you do it. The first step is to call the limit y. Okay, we're going to call the limit y. Why do you think I'm creating an equation all of a sudden?
Because we're going to do logarithmic.
I'm going to do a log. And the reason I'm going to do a log is because I really want to get that x out of here. I want it down from up here. All right. So now I bring in a natural log on both sides. Now be real careful, everyone, because I'm not doing any differentiation, logarithmic differentiation or anything yet. I'm just bringing in a log. Just hang tight. Hang tight, hang tight. So there comes the natural log on both sides. We are allowed to take the natural log and pass it through the limit. Technically, the natural log's on the outside, but there's a limit law that we covered way earlier in this class that allows you to pass the limit, the log through the limit. And now I can bring the x out in front of the natural log. Here's the x, natural log, cosine 1 over x. There we go. What that has done is it has now created something where I don't have that x up in the power. Agreed? Let's just run the limit again. Let's just check the limit to see again what happens. Be careful. I keep saying be careful. I guess you have to be careful all the time. So let's run the limit. Where is this going?
Infinity.
Infinity. Okay. Times. Now, this part right here. We did this earlier, but there's a little bit of a difference here. 1 over x was headed to where?
0.
0. Okay. And then I have cosine of that. Where's cosine of 0 headed?
1.
1. But now I have the natural log of it, right? Natural log of 1.
Okay, just check. That's 0.
The natural log of 1 is 0. The natural log of 1 is 0. So this is headed towards 0, isn't it? So we know how to do those, don't we?
Yeah, we just drop 1 down to the bottom.
Drop 1, right? So we just did something like this in the previous. So we should be able to handle the right-hand side now. So this now becomes natural log. Haven't done anything on the left. Nothing. Nothing. I just left it alone. Natural log y equals. Okay, here we go. I'm going to drop the x down. So I'm leaving the natural log and cosine of 1 over x here. And then I'm going to have on the bottom, what's on the bottom? I'm dropping the x, right?
1 over
1
x.
over x.
Over
yeah.
x. Okay, there we go. All right. Now you can check it for yourself if you'd like. If we run this limit now, the top heads to 0. Why 0? Because it's the natural log cosine of 1 over x. 1 over x goes to 0. Cosine of 0 goes to 1. Natural log of 1 goes to 0. So I know the top goes 0. And the bottom is fixed over infinity. Fixed over infinity goes to 0. So now I have 0 over 0 and L'Hopital is in play. Right? L'Hopital is in play. So natural log y equals, I need to tell you I'm doing L'Hopital. Ooh, I have to take derivative of the top.
That should be negative sine 1x, 1 over x over cosine of 1 over x.
I'm going to do that. I'm going to do a little slower. I'm going to go derivative of natural log of something is 1 over it. Sorry, I just got a delivery at the house. They ring the doorbell and the dogs are barking. Oh, enough. All right, so the derivative of natural log of something is 1 over it times the derivative of what's inside, chain rule, negative sine of 1 over x. And then times the derivative of what was inside of the cosine, negative 1 over x squared. All over the derivative of the bottom, which we've done now 3 times, negative 1 over x squared. These cancel. Are there any questions on that derivative?
Sorry, I have a question.
Yes.
How'd you get 1 divided by x?
How did I get what?
The 1 divided by x.
Okay, in this problem right here, I had infinity times 0, right?
Mm-hmm.
So anytime I see that, I pick one of these two and I drop it to the bottom. And so I took the x and I wrote it on the bottom as a 1 over x. It'll always be the reciprocal of whatever this is on the bottom. You just have to think like, if I took this 1 over x and I flipped the x back up, it would just become this, right, on top. So I'm just pushing it down as 1 over it to get the limit to go to 0 like I want. You're kind of nodding like you're being agreeable. Do you understand that or not? Look, here, let me do it this way. Let's say I had the number 2 times the number 3. Could I rewrite that as 3 over 1/2?
Yes, yeah.
Okay, because the 1/2 would flip up and just become a 2 on top. That's exactly what I'm doing. Instead of that, x times 3, I could rewrite that as 3/1 times x, because the x would come back up and just become this, right? That's exactly what I'm doing here. I have something times this, so I'm just going to rewrite this over that, 1 over that. Does that make more sense? The reason we do it, though, is that it turns, instead of this going to infinity, when you write it on the bottom as 1 over it, now it goes to 0. Okay, everyone's okay on this derivative? Okay, so derivative here, some chain rule, cancellation, and now let me run this limit again. See what happens. As x goes to infinity, 1 over infinity goes to 0. Cosine of 0 is 1. So that becomes, let me do a different. This right here is going to turn into a 1 times, let's see, 1 over infinity turns into 0. Wait a minute, what's sine of 0?
0.
0. Okay, so I have minus or times -0, but that's just 0. And that's all that's over there, right?
Yep.
That's it. Okay, but now our answer is not 0. Be careful. Our answer is not 0. Our answer is not 0. Watch. This is equal to what? What's the left side?
Natural log of y.
Natural log of y. Okay. Now, this means natural log of y has to be 0, doesn't it? How do you get y? Because remember, the original problem, y is what we're looking for, right? What's y? What's y, everyone? Well, I need to get y out of the natural log. So I need to come in with e on both sides, don't I? So e to the natural log y equals e to the 0. So that means y must be 1.
1. Oh, that's a,
That didn't do, Josh, what we thought, huh? Josh, I was kind of with you on that. I thought this one might go to 0.
Yeah, that did not do what I thought it was.
So
Yep.
here's what I'm going to do, because this was the original limit, right? Cosine of 1 over x, all of that to the x. I'm going to graph it, the whole thing. So that means I'm going to take this whole thing here and raise the whole thing to the x and zoom out. There's the graph of it. And notice that as you go to infinity, what that graph does, it heads to 1, doesn't it? So it's, again, there was this tug of war happening, right? The tug of war was, the base was like, I want to be 1. And then the exponent was like, no, I want to make you bigger, right? And then Josh pointed out that this was trying to be 1, but the numbers were smaller than 1. So big power on a number that's smaller than 1 should actually get smaller and go to 0. But it didn't happen. This guy won. This cosine 1 over x won. Okay, he overpowered this power, this exponent. Or they settled. I mean, they settled on 1. Interesting. Okay, let's say that's it for today. Let me look real quick at your homework to see what. I mean, I don't know how many of you are actually going to do homework, because the test is 2 days from now, but
yeah, to be honest, I'm probably going to do my review.
yeah,
Put the
I think
homework
we will
off for
need
the
to go do
weekend
that.
or something.
Let me go look though at the ebook real quick. Where are we? 3. So we jumped a few sections here. We're actually in 3.7. So we're not going to do 3.5 or 3.6. That's okay. We picked that up in Cal 2, so you don't need to worry about that. Let me look at the exercises for this, because you can't do this whole homework assignment yet. I need to look at what the homework assignment says. Okay. So pretty much if you look at this homework, problems 1, 2, 3, all of these are fractions. So all of these are going to be like 0 over 0 or infinity over infinity, the first few. And you don't really run into anything until you get to, wow, okay, see, they get more complicated. So, all right, let's just say that. Let's just do nothing past, well, these are 0 times infinity ones. Nothing past 28. So if you're going to do the homework for this, don't go past 28. So don't go past 27. Only go up through 27 if you're going to try any of it. Which I'm betting a lot of you are just going to get ready for the test. But if you're, looking ahead or after the test is over, you want to start doing the homework for this. If you try and do these right here, you're going to have some issues because we haven't talked about those yet. All right. There's still more to do.
And I'm also assuming free reign on the homework for 3-3 as well.
Yeah, 3-3 is now, go for it,
Okay.
Because the last ones there were the logarithmic differentiation, which is what we started class with here. What was that? 3-3 exercises. Three, 52, 53, 57. So 52, 53, and 57. These three can all be done with logarithmic differentiation. They even tell you use logarithmic differentiation. But yeah, you can do that here, here, and on 57. This is like the quiz problem I gave you. Cosine x to the x. All right, well, we have a test on Thursday. Make sure that you're here on time. Make sure that you've slept and you've eaten food and that you're ready to go. I'll be sending the test just like the last two exams, right? And you'll have to upload your work and your camera is going to be set up and we're not going to have any issues, right? Right, okay. All right, so I'm going to send everyone the notes from today and I'm going to upload the review solutions. Like I said, I haven't gone through them. So if you find something, let me know if it's like obviously out of place. Just send me an email or something so I can go look at it. Anything else? Y'all sure you want the solutions? I don't have to if you don't want to. I don't want to force you to. Wait a minute, what the heck?
Will be helpful for sure.
Zoom notes. Exam 3 review solutions PDF. Okay, there goes the review solutions.
I had
You're
a
free to go.
question.
Yeah.
On problem 18 of the review for like problem A, I did logarithmic differentiations. That are allowed to do?
Let me look at it. Hold on.
Okay.
Section PDF. Okay, so the notes from today are there. And okay, you're saying on the review, which one? 18?
Problem 18.
You could do that. Yes, you could. I think it's a lot more work, but yes, you could. It's not, it wouldn't be wrong.
Okay. Thank you.
Actually, it turns out to look like the same answer, at least for number 18A.
Yeah.
18A is real clean, but this one.
Oh, right. You just use
little
exponent.
bit of minor stuff you have to worry about, but yeah, you could.
For half a second, I was saying they're looking at trying to remember how you'd even do that without that. And then I remembered, oh yeah, there's a rule.
Yeah.
Yeah.
Remember
to be honest, the exponent rule tripped me up harder than the log rule.
Yeah, the review when I sent it out, I said your exam will definitely not be this long, right? Okay, I mean that's clear. There's no way it's this long, but I haven't made the exam, so I can't tell you how long it's going to be. I do know that there will be related rate problems. I gave you, a couple just to kind of give you a variety. You know, this problem required a triangle. This one required a triangle with part B, I had to use the angle. This one was similar triangles. This one was just a mess, 17. This came out of the book, the problem like this, so I didn't make that one up. This one I made up. This one there's not like one in the book like this, so I made that one up. So it's a bonus problem. Actually, I thought 18 was easier than 17, to tell you the truth. When I worked it out, 18 was much cleaner than 17 was. So, all right. Anything else?
Or I kind of wanted to ask.